Hello good people, I am tasked with calculating delta G for this reaction. Whenever I am faced with a problem, I tend to go back to stoichiometry, see if that will help me in some way. So in this particular reaction equation, it seems that everything checks out. I have one copper on the left, one copper on the right, one iron on the left, one iron on the right, and two positive charges on the left and two positive charges on the right. That means that stoichiometry alone will not help me this time. So now I need to think about the ways in which I can calculate delta G. Well, I could do this thing. I could sum up all of the delta G of products and then take away all of the delta G of reactants. I could also relate delta G to the cell potential, and I could relate delta G to the equilibrium constant K. So I looked into my textbook, the way you might gaze into a crystal ball, I suppose, to see if it will help me in some way. I could not find the equilibrium constant K, which means I cannot use formula number 3. I have then looked at the back of the textbook, where you can find all the nice thermodynamic values, such as delta G, and I could find the delta G for iron and copper, which are 0, and I could also find delta G for iron 2+, which is negative 85 kilojoules per mole. However, I could not find the delta G for copper 2+, which means formula number 1, for now at least, is out as well. That leaves me with formula number 2. And it's a good thing too, because my textbook does have standard reduction potentials for copper 2+ and for iron 2+, and I can use those to figure out the cell potential. How do I do that? Well, we need to firstly copy this equation. Let me just do that, hopefully correctly. Copy, paste, move it down here. And then we are going to split this reaction equation into our half reactions. So I will have iron solid going to iron 2+, aqueous, and the other half reaction is copper 2+, aqueous, going to copper solid. When I have my half reactions, it's always good to have them balanced. So the number of atoms is fine, however, the charges are not balanced. When we look at the iron, on the left we are neutral, on the right we have 2 positive. So a way of making this 2 positive neutral is by adding 2 electrons. Similar story with copper, except this time on the left we have 2 positive and on the right we are neutral. So a way of making this 2 positive neutral is achieved by adding 2 electrons. Fantastic. Now I can see that these 2 electrons will cancel out, and if I sum up these 2 reactions, these half reactions, I will get my starting reaction equation. Now you may wonder, why the bloody hell did I do this? What was the point? I seem to be going in circles. And to a certain extent, yes I am. However, by doing this step of using the half reactions, I have figured out the number of electrons involved in my process. And that is something I need if I want to use equation number 2. So I have figured out that the number of electrons used in the process are 2. But I'm getting ahead of myself because I need to figure out the cell potential. How do I do that? Well, the cell potential equals the standard reduction potential of the cathode minus the standard reduction potential of the anode. Or, I could also say, the standard reduction potential of the reduction minus the standard reduction potential of the oxidation. This means that I need to figure out what is being oxidized and what is being reduced. And I can do that by using the oxidation numbers. So copper 2 plus, the oxidation number of any ion, is the charge of the ion, which means it's 2 plus, plus 2. The oxidation number of iron solid is 0. The oxidation number of copper solid is 0. And the oxidation of iron ion is plus 2. So from this I can see that the oxidation number of copper was reduced. So copper 2 plus is undergoing reduction, and iron is undergoing oxidation because its oxidation number has increased. So I will write that here as well. My iron, that is my oxidation side or my oxidation half reaction, and my copper, that is my reduction half reaction. And using the mnemonic red cat and an ox, although that's not exactly a mnemonic, just a way of remembering things, I can say that this is my cathode and this is my anode. So now I can use these values. If only I knew them. Well, I do not know them, but I can look them up. And if I look into my textbook, I can see that the standard reduction potential for iron is negative 0.44, pardon me, negative 0.44, and the standard reduction potential for copper is positive 0.34. So now I can use these values down here. So I have positive 0.34, that is my reduction, my cathode, minus negative 0.44, that is my oxidation, my anode, and that will give me positive 0.78 volts. Let's not forget the units. Okay, so now I have my cell potential. I also have the number of moles involved, and the Faraday, well, the Faraday is a constant. So I'm almost ready to use my formula. Let me just copy it and bring it down here. Copy, paste, move it a little bit further down. Let's move it here. Fantastic. Okay. So what is my N? Number of moles of electrons involved in the process. So I have figured that that is 2. So 2 moles of electrons. The Faraday constant is a constant, and its value is 96,485 joules per mole. That's not how you write M. Per volt times mole electron. And my cell potential, I have just calculated, is positive 0.78 volts. I can use those values here, so I will have, let's use the appropriate color, negative 2 moles of electron multiplied by the Faraday's constant, 96,485 joules per volt mole electron, multiplied by the cell potential, 0.78 volts. And certain units will cancel. So this mole of electron and this mole electron will cancel. This volt and this volt will cancel, and I will be left with joules alone. all that remains is to plug in the numbers. So my value will be negative. If I use the calculator up here, 2 times 96,485 times 0.78 is equal to 150,517 joules, or we could round that to negative 151 kilojoules. So the change in Gibbs free energy for this process is negative 151 kilojoules. Now sometimes you might see this number written also as mole of reaction. What does that mean? Well, in essence, it just means that you will have negative 151 kilojoules for every mole of this whole reaction. Sometimes when we are lazy, we tend to forget this reaction and we just write negative 151 kilojoules per mole. So you need to be very clear about what this mole talks about. So it talks about mole of reaction. That is all, and I will see you on the flip side.